Alright, so in this episode we're going to be doing an example where we model a electric field of a point charge configuration using the material that we went over in episode 1. So let's jump over to the whiteboard and get started. Okay, so here you can see we have the following example where we have two source charges, plus q and minus q, in the xz plane, particularly on the z axis. They're separated distance d apart, equidistant to the origin relative to one another, and we want to model the electric field at the test point marked on the x-axis. Okay, so before doing any math, let's actually just examine this configuration conceptually. From our positive source charge, we'd expect an electric field to point in this direction away at our test point. And then similarly, for our negative source charge, ignoring the positive one, we would expect field lines to point towards our negative source charge here. So what we can do now is we can apply superposition to inspect what we would think our electric field's direction to be in. And we would expect it to be pointing downwards, if I could get this ruler to go properly. There we go. And we can draw a vector for where we would expect our electric field to go, and we'd expect it to go downwards in the minus z hat direction. And this is really important because once we get into the nitty-gritty of doing the math, we want to make sure that our conceptual understanding is agreeing with our mathematical interpretation. Now, since we have two point charges in this configuration, we're going to need to use this following equation here that we discussed in episode 1, and because of that we're going to need to set up two curly r vectors. Okay, so let's go and work through establishing two curly r vectors. Okay, so if you recall, our curly r vectors measure up from our source charge to our test point, or to a test charge. And so in this case we're going to have two curly r vectors, as I already stated, and curly r vector 1 is going to go from our positive source charge to our test point, and then curly r vector 2 is going to go from our negative source charge to our test point. So now we need to establish these curly r vectors mathematically, and to keep everything arbitrary, we're going to define curly r vector 1 as x hat minus d per 2 z hat, and then for curly r vector 2, it's going to be defined as x hat plus d per 2 z hat. Okay, so now that we have our curly r vectors established, let's use our equation and expand out our electric field equation to just begin to look at what our electric field equation is going to end up looking like. Okay, so we're going to have 1 on 4 pi epsilon naught times the quantity of our positive source charge divided by the magnitude squared of curly r vector 1 in the curly r 1 hat direction, minus, or I guess in this case plus, the negative source charge divided by curly r vector 2 in the curly r 2 hat direction. Now the minus sign in here comes from the source charge being negative. Remember, this is a summation, so if we had two positive source charges, this would be a plus, but we have to take into account the sign of our source charge. Now I want to quickly discuss how we're going to find our curly r1 and curly r2 hats. If you recall, a vector has both a magnitude and a direction. We have our curly r1 and 2 vectors already established. So the way that we're going to get our direction is we're simply just going to take our curly r vector and divide by the magnitude of our vector. And this works out really well because we already need the magnitudes to get the magnitude squared for our equation here. So now when we establish our curly r1 hat and curly r2 hat, we're going to get the following. For curly r1 hat, we're going to get x hat minus d per 2 z hat divided by x squared plus d squared per 4, and that whole quantity in the denominator square rooted. And then for curly r2 hat, we're going to get x hat plus d per 2 z hat, because that is our curly r2 vector, and then in the denominator it has the same magnitude of x squared plus d squared per 4, and that whole quantity in the denominator is also square rooted. Since we already found the magnitudes of our curly R1 vector and our curly R2 vectors, it's really easy to find the magnitude squared of both of those vectors. So our curly R1, the magnitude of our curly R1 vector is going to just be x squared plus d squared per 4, and then we're going to get the same exact result for the magnitude squared of our curly R2 vector. Now we have everything that we need, and we can plug all that into our electric field equation, and we're going to get 1 on 4 pi epsilon naught times one big quantity here, q on x squared plus d squared divided 4 times this subquantity xx hat minus d per 2 z hat divided by x squared plus d squared per 4, and that denominator square rooted, and then minus q divide x squared plus d squared on 4 times another subquantity xx hat plus d per 2 z hat divided by x squared plus d squared per 4 square root. Now, in the post edit, I noticed I made a small typo, and I just squared that second value value's denominator. It should be square rooted, so just take note of that. From here we can do some algebraic simplification to get that our answer is 1 on 4 pi epsilon naught times the quantity negative qd on x squared plus d squared on 4 quantity to the 3/2 power, and all of that is in the z hat direction. And again, our inspection at the beginning paid off because we got a minus z hat direction out at the end, so we know that our conceptual understanding is now in agreement with our mathematical understanding, so we know we got the right answer out. But that'll do it. That is how you model the electric field for this certain configuration. If you have any questions, feel free to leave them in the comment section down below, and I'll see you hopefully for episode 3 or possibly another video.